All right, so the next experiment is on bromimetric analysis, and that is the use of bromine in the assay, all right, in the determination of organic compound such as phenol, then the alkenes and other organic compounds. Now, we'll actually talk about this practical is on assay of phenol. The practical is on assay of phenol. Is that okay? So have it as assay of phenols. Is that okay? Now, at the end of the day, what are we actually talking about? What is used for the assay of phenol? Now, what is used is bromine. And I've said that this bromine is used for determination of organic compounds such as phenol, right? And alkenes. Of course, you know how they are used for determination. You said they use bromine to actually confirm bromine water to confirm the presence of what alkene, because it decolorises the bromine water. All right, so we can actually use it also for assay of what? Phenol. Now, they actually do this in two ways. Now, they may ask you, in what two ways do bromine actually add or carry out its reactions with organic compound? Now, it can actually carry out substitution reaction on phenol. Is that okay? Substitution reaction on phenol or on aromatic compound generally, but most times phenol. How is this reaction like? You have the phenol, of course, which is hydroxybenzene, right? OH plus 3 molecules of bromine. Is that okay? Now, at the end of the day, this is going to give us the phenol and then the bromine, since the phenol is an autopara director. You know what autopara director is now? We said that if an electrophile is coming in the presence of another group, depending on the nature of the group present there, it will either direct it to the auto-para position or to the meta position. So this OH is an auto-para director. Reason because it activates the ring. This has lone pairs of electrons, which actually activates the ring. So at the end of the day, bromine will be directed either to this auto position or to this auto position or to the what? To the para position. So we are going to be forming 2, if you want to count, this is 1, 2, 3, 4, 5, 6. So this is 2, 4, 6. How many bromine? 3. So you call it tribromophenol. So 3 molecules of bromine or bromine actually react with phenol to form 2, 4, 6 tribromophenol. This is one way by which bromine actually reacts with organic compound. And then secondly, by addition of bromine atom to unsaturated hydrocarbon. Now, this is our normal addition reaction. If you have unsaturated carbons like alkene, if you have something like this, I believe we learned things like this, then you have BRO2. We are told that this can actually add, and then you are going to form something like this. You have all these bonds present, and then you have bromine. Here you have bromine. Is that okay? So that is the product that is going to form. So from the unsaturated, going to form a weak dihalide. Is that okay? So these are the two ways. Now you may be asked, what are the two ways in which bromine actually react? By substitution reaction with phenol, and by what? Addition reaction with alkenes. It could be alkenes. It could be what? It could be alkyne via addition reaction. Is that okay? Now, we want to use bromine to actually what? Assay phenol. We want to use bromine to assay phenol. Now the equation of reaction is what I already drew on the board. The equation of reaction is what I already wrote on the board. But at the end of the day, there's something you need to know, that bromine is not stable. If you prepare it just like that, it will change to something else. Hence, you prepare it when you need it. That is in situ. Are you getting it? And the way to prepare bromine in situ, because you want to actually react bromine with all these things, Abi. So the preparation of bromine is prepared in situ by reacting, take note, by reacting potassium bromide and bromate. Now, but the potassium bromide, you are not going to write the KBRO plus KBRO3. This is potassium bromide, this potassium bromate, plus, let's say, HCl. These are the reagents that are actually used. But you are not going to write all this. Rather, you write only the ionic form of it. Is that okay? So the ionic form of it usually contains the bromine ion. Let me start with this one first. Bromate. So bromate ion will be something like this. 3 minus plus. Then we have the bromine ion plus what? H plus, to give us, now you already know that these three things are the things, because you may be giving this reaction to balance. You already know that these three things: potassium bromine, potassium bromate, and HCl. Of course, the bromine we give the bromate we give the bromate ion, bromide we give the bromine ion, and HCl we give H plus ion. Now this is going to form a bromine molecule, which is bromine molecule, which is BrO2 plus water. Are you getting it? It's going to form bromine molecule plus what? Water. But now you have to note something. Depending on the nature of bromine you need, that is how you are going to balance this equation, depending on the amount of bromine that you actually need. Now, of course, you see that in the assay of phenol, come back here, you see that we actually need 3 molecules of what? Bromine. Is that okay? So if you want to produce 3 molecules of bromine from this reaction, what does that mean? First of all, first thing first, you have to add 3 here, right? For us to now have 3 molecules of bromine. And if we have 3 molecules of bromine, it means we have to balance every other thing here. Now, how do we balance every other thing here? It's very, very easy. Now, 3 times this will give us how many? Will give us 6. Abi, so we have 6 bromine on this side of the reaction. Now look at H2O. Can you see that here you have how many oxygen here? 3 oxygen. But here you have how many oxygen? 1. So let us balance the oxygen by putting 3 here. Is that okay? Now, if you do that, you will agree with me that we are now having 3, 3. This part of the equation, we can now use it to balance this side. Now, how many hydrogens are you having here? If you now count these 3 oxygen, 3 oxygen. How many hydrogens are you having here? The hydrogens here are 6. How many are you having here? The hydrogens here are 1. So you have to add 6 here. Is that okay? Good. Now that you have balanced that, the next thing is to balance the bromine molecule. The bromine here, they are how many? They are 6. Here you have 1 bromine here, and then you have 1 here. How do we make this to be 6? We add 5 here. Is that okay? So we are going to add 5 here. This equation now is now balanced. Is that okay? So that is how you actually balance. Now let us assume you need 2 molecules of bromine, as in the assay of isoniazid. Now, what do you think the equation of reaction would be like? The equation of reaction, that one now you need 2 molecules. I'm just talking about another practical generally. So that one now will be, we are still using our BrO. That is one thing I want you to understand, that the amount of bromine that you need will determine the reaction you are going to write. Plus, of course, H plus Because what did I say this is going to give to us? This is going to give us Br2 plus H2O. We have to balance this equation. Now we need 2 molecules of Br2. So you put 2 here. Is the equation balanced now? No. Now, if you look here, we also have 3 oxygen here, right? But here you have how many oxygen? 1. So we also need to add 3 here. Is that okay? All right. Now, in this case, if you look here very well, you have 6 hydrogen here. So we also need to add 6 hydrogen to this part of the equation. Is that okay? Now, the last thing you need to balance now is your bromine. How many bromines do you have here? You actually have a total of 2 times this is how many? 4. Is that okay? But here, how many are you having? You are having just 2. So you need to add 3 here to make it complete how many? 4. Is that fine? So you are having this as the equation of reaction when you are actually talking about using 2 molecules of bromine. Now, listen. This reaction, it's actually a back titration experiment. What do we mean by back titration? We are going to react the bromine in excess with phenol. See how the back titration is and the principle behind it. You want to react phenol with bromine, Abi. You have this as your phenol. Let's say this is your phenol. Now, you want to react phenol, right? Now, you want to react bromine with phenol. So this is your phenol. This is your bromine. Now, listen, see what the idea of back titration is. You have bromine, you have phenol. We put phenol in excess. When you say you put phenol in excess, let's say phenol will be like, you put like 10. And then you now react phenol with what? Bromine. Is that okay? Or let's say phenol is about 10. Let's use it 10. Then you now react phenol with what? Bromine. Now, having reacted phenol with bromine, some of the bromine will be used up by phenol. Some of the bromine will be used up by what? Phenol. Now, listen. You cannot directly get the amount of bromine that was used up by what? Phenol. You cannot directly get the amount of bromine used up by phenol. Although you have 10 here, you cannot get the amount. Now, after this whole thing, let's say this is phenol. This is, you add bromine, you add this 10 bromine. And out of the 10 bromine, let's say phenol use some of the bromine, but you don't know the amount of bromine that is actually remaining. Phenol will not use all. Phenol will use only part of it. But you don't know the amount that is remaining. So you are now going to take that bromine from here, which is the remaining bromine, and then use something else, another practical entirely. Are you getting it? To calculate the amount of bromine remaining. Let us say you now get the amount of bromine remaining to be 4. You know that the initial amount you put was how many? 10, right? Like I told you, you cannot measure directly how many phenol has used. But let's say you use 10 initially, and then the remaining one now is now 4. Now, what does that tell you? That tells you that phenol used how many? Phenol used 6. Are you getting it now? By so doing, you've been able to calculate the amount of bromine that was utilized by what? Phenol. So it's an indirect titration, or we can call it a what? A back titration experiment. Is that okay? Back titration. We did this in when we were in year 2, where we ran blank. Are you getting it now? So that is what we actually do in this particular experiment. What we are going to do is, first of all, react phenol with bromine, take the unreacted bromine, get the amount of unreacted bromine, then from getting the amount of unreacted bromine, you actually be able to get the amount of bromine that was what? Reacted. Is that okay? Now, how do we carry out this experiment now? First of all, you are going to have 2 titer values. One is for the blank. Is that okay? While the other one is the main titration. Now, the blank will always be greater than the main titration. But in the blank titration, you are not going to add phenol, while in the main titration, phenol will be part of it. Let us say you ran your blank, and your blank gave you 27. I'm just saying, and the main titration gave you 25 ml, right? 25 ml. This one is without phenol. The blank is without phenol. Why this one is what? With phenol. Now, at the end of the day, to get the amount of bromine that reacted with phenol, to get the amount of bromine that reacted with phenol, what you are going to do is to subtract your blank from the main titration. So this is going to give us 27 minus 25, which is equals to 2 ml. So this 2 ml now is the amount of bromine that reacts with what? Phenol. The 2 ml is the amount of bromine that reacts with phenol. Now, another thing that is making this practical intricate is the bromine. Recall that we had an equation here which actually liberated bromine, right? Which is this. And then I told you that phenol reacts with bromine. Is that okay? Phenol, told you earlier that phenol will react with what? With bromine. But the bromine is in what? In excess. So you are going to carry out another practical to determine the amount of bromine remaining. Is that okay? After adding it with phenol. That one now will tell you the amount of bromine that is what? Remaining. Is that okay? Now that amount of bromine that is remaining, you cannot easily detect it. You cannot easily carry out this experiment. So what you usually do most time is, after reacting this and this, listen though, you take that solution. You know that solution will contain excess bromine. That means the amount of bromine that did not react, because bromine is going to react with phenol. But at the end of the day, bromine will still be in excess. So there are some bromine in the solution mixture. You are going to now react that solution that contain bromine with hydrogen halide. 2 molecules of what? Hydrogen halide. Of course, this one will displace the halide from here, so that you are going to have 2, because bromine is more electronegative than iodine. So you are going to have 2 HBr plus what? Iodine. Now this iodine now can easily be assayed with sodium thiosulfate. So you are going to have assay with what? Sodium thiosulfate. Now when iodine is assayed with sodium thiosulfate, it's going to give us sodium iodide, 2 molecules sodium iodide plus this same sodium S2, but this whole thing will change to S4O6 if you balance the equation. Now sometimes for me, I just feel this practical may not come out, but these equations may likely come out. Are you getting it now? So you should always take note of this equation. So to get the amount of bromine that did not react, what you will actually do is to titrate the iodine with sodium thiosulfate. That is how you get the amount of bromine that did not react. Titrate iodine with what? Sodium thiosulfate. Is that okay? To get the amount of iodine that did not react, the amount of bromine that did not react, titrate iodine with sodium thiophosphate, because it's more like the iodine represents bromine in this case. So anything you get for iodine is still the same thing as what is present there for what? For bromine. Is that fine? So that's what we are going to do for this particular experiment. And in the first case, you have just the iodine with sodium thiophosphate. Are you getting it? Just the iodine with sodium thiophosphate without phenol. That one now will give us your blank. Then the second case, you are going to have the iodine with sodium thiophosphate with phenol. To tell you, that one now will not tell you the amount of what? Excess bromine that did not react, that actually reacted with sodium thiophosphate. And then at the end of the day, you subtract to get the amount of bromine that is actually present in the titration. And then having done that, the next thing is your Milli equivalent. Now the Milli equivalent may be given to you. The Milli equivalent, you get it from the equation of reaction. So you have something like this. This is phenol. All right. Phenol is what? Phenol is OH. Phenol is C6H5OH. Are you getting it? Now phenol reacts with how many molecules of bromine? 3 molecules of what? Bromine. And how many hydrogens? 6 hydrogens, corresponding to 6 hydrogen ions. But what we are interested in is the reaction between bromine and what? Phenol and 3 molecules of bromine. So we can say that 1 mole, listen, we can say that 1 mole of 6H5OH will react with 3 mole of BrO2. Told you that 1 mole of this is still the same thing as the molar mass. Molar mass of phenol is about 94.11 gram. Of C6H5OH will give us 3 mole of BrO2, right? Which is, now this 3 mole, what is mole? What is molarity to start with? Molarity, capital letter N, is number of mole all over volume in liters. But now you are calculating for milli equivalent. So we can say number of moles will be equals to molarity times volume in liters, right? How many moles are you having here? 3 moles. So we can say N. For our number of moles to be 3, our molarity can be 1 mole, then the volume can be 3 liters. Because N is our number of mole. And what we have here is 3. You can say, okay, let our mole be 1 mole and the volume be what? 3 liters. Because 1 times 3 will give us what? 3 mole here. Is that okay? So that at the end of the day, what you are going to have would be this 3 liter. You are looking for milli equivalent, so you must convert it to what? To milliliter. So this is 3000 milliliter. So that what you are going to have here will be 1 mole, 3000 milliliter of what? BrO2. So instead of putting 3 mole here, you just put 1 mole, 3000 milliliter. This 1 molar 3000 milliliter is still the same thing as 3 mole. Are you getting it? This N here is the same thing as your number of mole. Is that okay? This N here is the same thing as your number of mole. And we can express number of mole as the molarity times volume. Since our number of mole is 3, we want a situation where molarity times volume will give us 3. And in that case, we can say let our molarity be 1 and our volume be 3 liters. But we are looking for milli equivalent. So liters will be converted to what? Milliliter. That was what we did here that made this one to be 3000 milliliter. So means this gram of phenol is equals to this. Now at the end of the day, what are you going to do? You divide by depending on the nature of the phenol that is given to, the bromine, the concentration of the bromine given to you in the experiment. Now if you check your manual, you discover that bromine, the amount of bromine given to you was 0.05 mil of bromine. So you convert everything here, this molarity, to 0.05 molar rather. 0.05 molar. Think so? 0.05 molar, yeah. So the first thing we are going to do is we must convert this milliliter to 1 mil. And one way I usually do the shortcut, just divide this one by 3000. Now anything you divide here, you divide here, but you must not divide 2 of them at once. If you divide 1 here, divide 1 here. If you divide this one, you divide this one. But you cannot divide this and this. You cannot divide 2 of them the same time and divide this. You only take 1 from here, 1 from here. So if we divide here by 3000, means we also divide here by what? 3000. Now at the end of the day, what do you think you are going to have? What do you think you are going to have? This is going to be, this cancels this, and then at the end of the day, you are going to have 94.11 divided by 3000. This will give us this will give us 0.03137 C6H5OH is equals to 1 molar 1 mil of BrO2. So we've gotten to mil, but we must get to that 0.05 molar. How do we get to 0.05? If you divide here by 20, it's going to give us 1 divided by 20 is going to give us 0.05. Check it. 1 divided by 20 is 0.05. But here, you can also divide here by 20. So anything you do here, you must do it here. So when you divide and cancel that, you are going to have 0.03137 divided by 20, which gave us 0.001569 C6H5OH to give us 0.05 molar 1 mil of BrO2. Now, what does this mean? This means that the 1 milliliter of 0.05 molar of this compound of BrO2 will give 0.001569 phenol. That is the meaning of this. 1 mil of this will give this. So you can now say that 1 mil of not phenol, 1 mil of BrO2 gave us 0.001569 gram of C6H5OH. Now, record the amount of phenol, amount of bromine that actually reacted with phenol. I told you that you get that amount by subtracting the blank titration from the main titration. Is that okay? And in this case, I say let's take blank minus main titration to be 2 mil. So it means 2 mil for this our reaction. It means for this our experiment, it means 2 mil of bromine actually reacted with what? Phenol. So if by standard 1 mil of bromine will react with this amount of phenol, therefore 2 mil of bromine will react with X gram of phenol. Do you understand? By right, 1 mil BrO2 react with this of phenol. Therefore, from our experiment, when you subtract 2 mil of this react with X, then at this point you cross multiply. This X now is going to give us 2 times 0.00159 gram of C6H5OH, and then X would be equal to 2 multiplied by 0.001569, and this will be exactly 0.003138 gram of C6H508. Yeah. So it means calculated weight. Now this will be our calculated weight for phenol. Is that okay? This will be our calculated weight for phenol. Now, if this is the calculated weight for phenol, what is the theoretical weight we are expecting? Now, you get your theoretical weight from the practical. Is that okay? You get your theoretical weight from the practical. So they say take 0.5 gram of sample in 250 ml of water. So if you look at the practical manual, it was stated there, that will give us the amount of theoretical amount of phenol we are expecting. So we have 0.5 gram in what? In 250 ml of water. Measure 25 ml. So what we actually used for this experiment is what? Just 25 ml. So if 0.5 gram is 250 ml, they now say out of this 250 ml, take 25 ml. We want to calculate the amount of phenol in the what? In the 25 ml. So we say 0.5 gram of phenol is present in 25 ml. 250 ml rather. 250 ml. Therefore, 25 ml would be equals to what? X. Now, at this point in time, cross multiply. This is going to give us, when you multiply this is going to give us 250 x 0.5 times 25. So divide by 250, divide by 250. When this cancels, x will be 0.5 times 25 divided by 250, which gave me here 0.05 gram. Is that okay? Who gave me here 0.05 gram. So that's the amount in that 250 ml that we actually pipetted, that we use to carry out our practice. Now, for the experiment, it depends on the amount you actually lifted from this 250 ml. And I discovered that the one we did in the lab, we didn't use the 25 ml, we actually used 12.5 ml. But the manual said 25 ml, but we used 12.5. So this will be 12.5 ml. Are you getting it now? Pending on they tell you the amount that you actually weigh. So that at the end of the day, this will be 250x will be 12.5 ml times 0.5 gram of phenol. So x will be 12.5 times 0.5 divided by 250. When we cancel this stuff, it's going to give us, divide 12.5 times 0.5 divided by 250. This will give us 0.025 gram. So it means theoretical yield of phenol, the amount we are expecting is 0.025 gram. However, the amount that we got from our practical is what? 0.003138 gram of phenol. So to calculate the percentage yield or the purity, percentage yield would be equal to the amount calculated with, which is 0.003138. Let me write it. 0.003138. Make sure this is correct. Yeah, 0.03138 divided by 0.025 times 100%. This is theoretical. Now, when you divide this, percentage yield is going to give you an amount. So your percentage yield would be equal to, what do you think the percentage yield will be now? To be 0.003138 divided by 0.025 times 100%. Percentage yield will give you around 12.5% approximately, or 12.6% weight by weight. So this is the amount of phenol that the percentage purity or the percentage yield of phenol. Is that okay? So that's basically everything for this experiment. It's quite a complex one that requires you to reason very well. However, if you know you may not be able to carry it before the exam, you can just leave it, because PCH can still shock you. So now they may ask, in the assay of phenol, why do we add chloroform? Now we add chloroform to dissolve tribromophenol. At the end of the day, you discover that they actually added chloroform. You added chloroform to do what? To dissolve the tribromophenol form, so that no iodine, you know that reaction involved iodine, no iodine or bromine is actually what added to, or is adhered to the precipitate, because it's going to precipitate this 2,4,6 tribromophenol. When you add chloroform now is just like a crystallizing agent. Are you getting it now? So that is that. All right. Say iodine partitions into the chloroform layer and impart visible color. It is necessary to shake well, since the thiosulfate will react only at the aqueous layer. Thiosulfate will react only at the aqueous layer. Iodine and bromine will partition into the chloroform layer. So it's more like solvent-solvent extractions and not even precipitation. You add the chloroform so that in case there is anything iodine also, those ones will go to the chloroform layer. Why the thiosulfate will only react with the what? Aqueous layer. And the aqueous layer is where this sheet here will be formed. Is that okay? So that is everything you need to know about this practical. And then that of isocyanide, we should just hope for the best.